Hello everyone, welcome back to the channel Mining Engineering. Today's topic Geographic Information System. We'll continue some more parts of lecture number 6. We have already discussed these things in the lecture number 6 part 1. We have discussed what are the problems which are associated with the representations. Some geographical phenomenon can have different representations at different scales and different levels of accuracy. Now we'll see what are the vector data structures and what is the spaghetti data model. Spaghetti data model is one of the simplest vector data structure. Each point, line, and polygon feature is represented as a string of x and y coordinate pairs. For example, take this thing. Here is one point, here is one line, and here is one polygon. And the point A, the x and y coordinates are on x-axis it is 2 and on the y-axis it is 4.7. So the point is represented by a pair of x and y coordinates. Similarly, for this line, the point here, this point it is 1 and 5.6. This is 1, 3.5. This is 1.6 on the x-axis and 3 on the y-axis. Similarly, 1.6 and 0.4. Similarly, for this polygon, these are the coordinates x and y coordinates pair for representing this polygon. Spaghetti data model problems. Sharing of common boundary or nodes are not possible. Special relations like adjacency, connectivity, containment, etc. are difficult to determine. For example, let us take this polygon A and this polygon B. This is polygon A and this is polygon B. And we can see the polygon A and polygon B are sharing this common boundary. Point the nodes x3, y3, x4, y4, x5, y5 and x6, y6 are the common nodes. However, here the polygon A has stored these points. Similarly, the polygon B has also stored the similar points. Shared boundary stored twice. So we have stored the same data twice. That is the problem. So we can say this is not a problem. What's the issue sharing the data twice? But the problem, the common boundary problem, may not look prominent for 2 or 3 polygons, but for a large GIS database with more than thousands of polygons, it is a significant issue. More data will consume. Again, there is another problem associated with such type of issues. If while digitizing the model, if there is some poor level of digitization, there will be formation of gaps between these two polygons. Here, the polygon A, polygon B is sharing this common boundary. However, due to the poor level of digitizations, we can see there is some gap boundary pulled apart between these two polygons, and that will create a major issue while calculating some more investigations about these GIS data structures. Special relations like adjacency, connectivity, containment, etc. are difficult to determine. Take this example. There are 3 roads, road number A, B and C, and there are 3 polygons A, B and C. While representing these 3 roads, road A, road B and road C, we can see, and the polygons A, B and C, we can say the polygons as well as the roads are intersecting with each other at many places. But here in this spaghetti model, we don't have any clue about their adjacency, connectivity, and containment. So it's difficult to determine through this spaghetti data model. Next one is the topological data model. Topology in GIS is a set of rules to express explicitly the spatial relationship between features. The three basic topological relationships are connectivity, area definitions, contiguity. Connectivity, arcs are connected at nodes. Area definitions, area is defined by a series of arcs. Contiguity, arcs have directions and left and right polygon. Spatial relations are easier to determine when compared with spaghetti model. Let's take the example arc A, that is from node B to node C, arc A from node B to node C, then arc B from node A to node C, arc B from node A to node C, again arc C, that is node C to node D. Where is C? This is C, is from node C to node D. Again arc D, that is node C to node H. Arc D is node C to node H. Like this, arcs sharing same nodes are connected. Here also, for the polygon, this is a polygon, arc A, left polygon to right polygon. Something which is beyond the boundary, that is called the universe. That's why that is represented by universe, from left polygon universe to right polygon universe. So let's see what is arc A. This is arc A, and there is no polygon on the left side. Also, there is no polygon on the right side. So the left polygon is universe and the right polygon is also universe. Similarly, for arc B, the left polygon is universe and the right polygon is universe. That is node B, the left polygon is universe and right polygon is also universe. Similarly, for C, the left also universe and right also universe. Left also universe and right also universe. Again, D, both are universe. Now let's see what is the arc F. Here in the arc F, this is arc F. Here the left is universe, that is something outside the polygon. However, in the right side there is polygon 1, and that is written here. Similarly for G, arc G, arc G, the left one is the polygon 1, the right one is polygon 2. Similarly, we can see both the attribute table and the map. Structure of nodes in a topological model. Points and nodes are first identified and defined by a pair of x-y coordinates. So nodes are first identified and defined by a pair of x and y coordinates. The node 1, the latitude and longitude; for node 2, latitude and longitude values. Arc node topology. Nodes are the intersection points where two or more arcs meet. Apart from the vertices which define an arc, they will also have a from node and a to node list. Connectivity defined as all arcs sharing a common node are connected. Polygon arc topology. Topologically connected arcs are used to define the boundary of the polygon features. Area is defined by polygon arc topology. Use arc and arc directions to combine polygons. Polygon A, number of arcs 3, arc list is A, D, and G. Left-right topology. For each arc, the identity of the polygons to the left and right of it are also recorded. Contiguity is defined as the polygons that share a boundary are deemed adjacent. Universe is an external area located outside the study area. So what are the advantages and disadvantages of raster and vector representations? Raster, the advantages are simple data structure, compatible with remote sensing and scanned data. The disadvantages are cell size determines the resolution at which the data is represented. Requires a lot of storage space. Projection transformations are time consuming. Network linkages are difficult to establish. In case of vector, the advantages are data is represented at its original resolutions and form without generalization, require less storage space. Editing is faster and convenient. It provides efficient encoding of topology. As a result, efficient implementations of operations that require topological information such as network analysis. Projection transformations are easier, and the disadvantage is location of each vortex is to be stored explicitly. Thank you.